In this video, I want to show you how you can use F equals ma along with concepts about circular motion to solve some new kinds of problems. So in this problem here, we have a car that's moving through a dip in the road, and we want to study the motion of the car as it's going through that dip, okay? So we have a 1,200 kilogram car. It's traveling at a constant speed of 25 meters per second, and it reaches the bottom of that dip, which is a 10-meter in radius, big, huge dip in the road, like a valley. And we want to know, first of all, what force is providing the centripetal acceleration, and what is the magnitude and direction of the centripetal acceleration. Okay, so step one, let's sketch it. So let's say the car is going on a flat road like this, and then I don't think I have a good drawing tool for drawing half of a circle, so I'll have to do it freehand. This might be ugly. Okay. That wasn't so bad. Okay, so there's my circular dip in the road, and then let's say over here, the road goes back to normal. And we know that there's the center of the circle, and this dip in the road is 10 meters in radius. And I'm interested in when my car is down at the bottom of the dip here. And when my car is at the bottom of the dip here, let's say it's moving left to right across the screen, it has a velocity 25 meters per second. Okay, so there's my basic sketch, just to wrap my head around the problem. The next thing I'm gonna wanna do is draw a free body diagram, as usual. Just a side note here, just because we're doing new kinds of problems here, don't forget that this all still fits into the basic F equals ma framework that we're doing initially. So I'm still using the same exact F equals ma procedure that we've been using for almost the entire course so far. All right, so let me draw the free body diagram off to the side here. And now we think about what are the forces acting on this object. So this has nothing to do with circular motion yet. This is something that you could have done earlier in the course. Just go through the different forces and figure out what are the forces acting on the object. So we've got certainly gravity is pulling the object downward. So we're gonna have there mg, good old mg. And we have this car is sitting on a road. So the road is going to be providing a normal force, contact force, which is going to be pointing upwards because that is the direction perpendicular to the road, which, by the way, now that we're working with curves, I should probably mention as a side note, when we say for the normal force that it's perpendicular to the contact surface, what if it's a curved contact surface? In this case, it's basically perpendicular to the tangent to the contact surface. So like if we drew a tangent line to the contact surface at the bottom here, it would be flat. So it's as if the car is sitting on a flat surface as far as the normal force is concerned, because the normal force wants to be perpendicular to its present location. It doesn't really care that overall the object is moving on a curved surface. It wants to be perpendicular to the surface that it is on at this instant in time only. Okay. So we've got the normal force pointing upward, mg pointing downward. Are there any other forces acting on the object here? And the answer is no, maybe surprisingly, because the object is moving to the right. So you might be saying to yourself, if the object is moving to the right, there has to be a force pushing it to the right that's causing it to move that way. Absolutely not. Absolutely not. If you're thinking that, you've fallen victim to the classic mistake in introductory physics, which is all the way back to the very beginning, Newton's first law of motion. You do not need to have a force in the x direction just because you have a velocity in the x direction. What's keeping the object moving in the x direction is its inertia, not a force. So there doesn't have to be a force in the x direction just because there's a velocity in the x direction. In this case, there isn't one. So all the forces are in the y direction, but the velocity is in the x direction, weirdly. But that's totally fine. So anyways, we have our free body diagram then. Next step is to turn this into an F equals ma equation. So let's do it. I only have one-dimensional thing here, so there's nothing special to do. All I have to do is write normal forces in the positive direction, mg is in the negative direction, and then that's going to be equal to what? Now here's where the circular motion concepts come in. Normally, previously in the course, we would normally just mindlessly write ma here. But in circular motion, you have to be very careful because we know actually quite a bit about the object's acceleration. We know that the object is moving in a circle at constant speed. So therefore, we know that the acceleration is centripetal, which means that the acceleration vector has to be pointing back towards the center of the circle here. So first of all, I can see that the acceleration is going to be pointing in the positive y direction. So it should be positive ma appearing in this equation. And furthermore, I know that this acceleration is a centripetal acceleration. If you want to, you might want to denote that by using a subscript c there to remind you that this isn't just any old acceleration. This is a centripetal acceleration. Okay, now since I know that it's a centripetal acceleration, I can plug in here if I want to that this is equal to m times v squared over r, which is then going to allow me to solve this problem. Namely, in this particular case, m is known, g is known, v is known, r is known. The only unknown is the normal force. So the normal force here is going to be mg plus mv squared over r. Okay. Now, I should probably go back and actually look at what the questions are that are being asked here. I've organized my thoughts about the problem. I've practically solved the problem. So what was I actually being asked to do? Question number 1, what force is providing the centripetal acceleration? Well, look, the centripetal acceleration is pointing upwards. Notice the acceleration is upwards. So the force providing that acceleration is going to be a force that's pointing upwards. So that would be the normal force. So the normal force is providing the centripetal acceleration in this case, which means sometimes we would call that a centripetal force, you know, the sum of the forces in that direction could be called the centripetal force. Centripetal force, by the way, I don't like to use that term. So I'm not going to use it because I find it confuses people, because when you say the term centripetal force, students think you're introducing a new force into the course. This is not a new force. This is just a term that describes the centripetal acceleration. So anyways, the normal force is basically providing the centripetal acceleration, or if you prefer, you could say really the centripetal acceleration is being provided by the normal force minus mg, if you want to be a little bit more mathematically minded about it. Number 2, calculate the magnitude and direction of this force. So the normal force we've already written down here is mg plus mv squared over r. So that's going to be 1200 times 9.8 plus 1200 times v is 25. Note that that's v, the good old-fashioned speed. That should get squared. Divided by r is the radius of the dip. That's 10. So then the normal force is 1200 times 9.8 plus 1200 times 25 squared, divide 10, and I got 86760 newtons is the normal force. And then if you want to, you can also do, you can also find Fn minus mg. The entire centripetal force would be equal to MAC. So that would be 1200 times 25 squared divided 10, 75,000. So the entire centripetal force, 75,000 newtons, and the normal force itself is 86,760. Okay. Then last question, conceptual question, explain why you feel heavier at the bottom of the dip if you're driving too fast. This goes back to the concept of apparent weight that we talked about earlier in the course. The normal force here is also equal to the object's apparent weight, which is how heavy you feel. So really what the question is asking is, explain why the normal force is higher if you're driving too fast. And once you spin it that way, it's obvious, because driving faster, that means the velocity is going to go up. But you can see if the velocity goes up, the normal force is going to go up along with it, because the normal force depends on the velocity. So if the velocity is greater, the centripetal acceleration is greater. And if the centripetal acceleration is greater, the normal force is greater. And that makes your apparent weight greater. So you're going to experience that. A more conceptual way of saying that is that since the acceleration is upwards, like if you think about this, if you think about your apparent weight as being like the force that your muscles and your bones have to exert to hold your body up, to hold your body sitting upright in the car, your muscles and bones now not only have to provide the balance for gravity, they also have to supply the centripetal acceleration. So that's why suddenly your body is being asked to supply a larger force to hold your body up, because your body actually has to supply that upwards force to give you the upwards acceleration you need to climb that dip. And that's basically the origin of why you feel heavier for a moment, why your apparent weight goes up on those dips. Big picture here, by the way, just to put this in context again, just notice I solved this problem, although this was like nominally a circular motion problem, I solved it using exactly the same F equals ma framework that you're already familiar with. The only difference is I knew something I could plug into the ma side of the equation, namely something about the acceleration vector that you didn't know before. But otherwise, this is a problem you could have solved earlier in the